Okay, we are live. Hello, everyone, and welcome to MLDon. Today is yet another exciting session on variational autoencoders, and again, we are here with my dear friend Khalil. Welcome, Khalil. How are you?
Hey, hi everyone. Good to be back here. We kind of missed you last week. But again, things happen. So let's pretend that didn't happen. Let's just kind of drive on because I think I'm excited about what Mehran is going to show off. So yeah, it's good to be back here.
Yeah,
Let's do it.
let's do it. Good to have you as always. So yeah, as promised, today we're gonna focus on one of the most feared parts of machine learning, that is the loss function of variational autoencoder. I mean, you look at it, it just terrifies the Jesus out of you. And then many people just, give up understanding it because, well, they say, okay, why do I need to understand this? There are codes that are already available. There are AutoML, modules out there that are available. Like, why should I even care about doing this? But you'll see as I go through it that, first of all, you need to understand the derivation, the components of the math to be able to actually implement it. You have to understand what expectation means. You have to understand what KL divergence means. You have to understand what probability distribution means in order to be able to actually implement this loss function while we actually code variational autoencoders. So that would be one of the advantages. The other advantage of knowing the math behind the story is that there are so many sort of basic components throughout this derivation that if you learn properly, it will help you in your implementation journey when it comes to implementing other modules, machine learning modules, such as generative adversarial networks, such as predictive coding networks, energy-based neural networks, and so on and so forth. So you can think about different parts of this derivation as like building blocks for understanding the math of other modules or other sort of algorithms, which would help you implement them much more easily, as well as make modifications to them. This is also very important. If you want to improve on a certain technique, a certain algorithm, you cannot do that unless you understand what the heck is happening under the hood. Okay. I've already shared a PowerPoint on our Discord server, MLDon. You already see the link to our Discord server in the chat. So if you click on it, you become members, and you can actually download the actual PowerPoint file under the announcements channel. But this is going to be basically the roadmap for today's session. Khalil and I will go through the very basics, the mathematical basics that you need to understand. Variational autoencoders, loss functions, derivation. There are so many little components that you need to know before you can actually start deriving it. And then in the second half, we actually start the derivation, and you see that, okay, like each part of the derivation sort of connects to some parts of the basics that we will have covered by then, okay? If it all sounds well and good to everyone, we're just gonna get started. So I'm gonna share my screen. Okay. Now, this is again, like sort of remembering from our past session, this is again a variational autoencoder. So we didn't really go through the math, like what these, distributions, P, Q, Z, X, what they mean. We don't really need to. Let's first understand the mathematical basics for now, and then we'll understand what happens under the hood. Now, there's some sort of, you can categorize the mathematical basics into, I would say, 4 main chunks if you want to understand the loss function of variational autoencoders. You need to get comfortable with logarithm and the properties of logarithm. You need to understand what a random variable is and what it means to take the expectation of a random variable, which has a certain distribution. It has a certain probability distribution. you need to get comfortable with KL divergence, what it means, what does the math mean, and how you can actually use it to sort of measure the difference between two distributions. And finally, we have Bayes' rule. Now, Bayes' rule is going to be the core sort of component of all of this derivation, and it appears everywhere, really. It's such an important and fundamental part of many algorithms, both in statistical learning and excuse me, and machine learning, that it would really benefit you well if you understand it properly. So let's start with properties of logarithm. Now, just as a reminder, a logarithm can be defined as, if you look at, maybe I should maximize this so you can get it bigger a little bit. Right, so log of something with base A equals B. I mean, I'm sure you've seen this notation of logarithm, but what it really means is this is actually tantamount to saying that x is equal to a to the power b. Now, let's just look at a very small example. Let's say x is 8 and base is 2, base of our logarithm. So in that case, if I say that the logarithm of x that is 8 and the base that is 2 is equal to what? Right? So it is effectively saying the same thing as x that is 8 is equal to a that is 2 to the power of what? So that's the b that we want to figure out. So in that case, b is equal to 3. Right? Now, they use logarithm for many reasons, but the main thing is, if you look at the plus on the top right-hand side here, you notice that as x increases, the growth in the log of x, depending, I mean, it doesn't matter what sort of base it has, whether it's base 2, base with the Euler's number, that is base e, or base 10, you can always see that as x grows, sort of the growth in the output of log sort of gets smaller and smaller and smaller. So that is a way to make certain functions more well-behaved so that they can't just go crazy. Like if you put x in f of x and f of x has this sort of exponential growth into like plus infinity as x grows, by applying log on top of that, you make it a little bit more behaved so it will not just go crazy insofar as the outputs of its values. And the other feature of, let's say, property of logarithm is that log of a with the base a is equal to 1. I mean, this is basically given based on this sort of explanation over here, right? So basically a is equal to a to the power 1. That is why that's the case. Now, we also have natural log. It's just the same as logarithm, but the only difference is that the base is Euler's number. And Euler's number is this value, right? And the two main properties, we will be using these two extensively today. Okay, so get comfortable with these two. One is log of a multiplication, right? That would turn into the sum of the logs. So log of u plus log of v. And you notice that the base doesn't change, right? And log of a division turns into a subtraction of the logs. Log of u minus log of v. Please keep these two in mind. We will get back to these and we will use them extensively today, okay? One other thing that I'd like to point out before we move away from this slide is that if you look at these logarithm plus on the right-hand side, so the only thing between these three that is changing is the base. So as the base is increasing, you notice that the growth of logarithm with respect to x gets slower and slower, meaning that if you increase x a little bit, you would have much smaller growth in this case than you would have in this case, and definitely in this case. So the base of the logarithm sort of dictates the growth rate of the logarithm, the behavior of the logarithm. Not that it matters in today's session, but just want to point it out just so you understand these values actually dictate the shape of these logarithms. And the other thing is, can you tell me what the logarithm of, let's say, 0 is? Maybe Khalil, you can venture a guess.
The logarithm of of 0, I don't know, 0
is actually not defined.
Interesting.
Yeah, because you see these logarithms, they never reach the y-axis. They sort of so let's say as x moves, let's say towards 0, the logarithm sort of moves towards minus infinity.
Oh yeah.
Yeah. And the other thing that I would like to say here is that the logarithm of 1, right? This is the funny part. With any base, doesn't matter, irrespective of base. Can you venture a guess what it's equal to using this definition?
0.
Exactly, well done. So it means that doesn't matter what the number is, if you raise it to power 0, it's always equal to 1. So these are some of the properties of logarithm that I wanted to share with you guys. Any questions here, Khalid?
No, more like a comment though. Like I tend to think of logarithms as a means to smoothing differences between numbers. As you know, you can see in your graph on the upper right hand there, the difference between 1 and 10 has been reduced to 0 and within the range 0 and 1. So anytime I think of logarithms, I think of them as smoothing functions, so just kind of make things more smoother.
Yes.
Yeah, so that's how I think about it.
Yes, that makes sense. So as oops, let me minimize this for a sec. Okay, so as we add to x, like x plus delta x, the value of the logarithm, like the amount of y, the amount of delta y that is added to it, as you said, it sort of gets smoothed out if you apply logarithm. That definitely makes sense. Now here, I'm going to talk about expectation, right? So this is, again, it might look really sort of, let's say, scary, but it's not, I promise you. I'll show you an example, a numeric example, to explain to you exactly what's happening here. But effectively, suppose you have a random variable. Now, the second I tell you I have a random variable, what it immediately means that it can take different values. Now, if it can take different values, it doesn't mean that you are totally clueless as to whether certain values are more likely than some certain other values. There is something called the probability distribution of a random variable that describes the likelihood of certain values appearing in that random variable compared to other values, right? That's called the probability distribution. Now, because a random variable is a random variable, you can never say, okay, what is the value of this random variable? Give me one answer. You can't, because it keeps changing. What you can ask, though, is, okay, of all the values that this crazy random variable can take, Can you tell me what my expectation should be about the possible values of that random variable? So what should I expect of all the faces and values that this variable is gonna get to itself? And that is a legitimate question. And that is the formulation that you see here, the expectation of a random variable. Now, suppose your random variable is discrete. Like, for example, it can be showing the values on the size of a die that you've just rolled. So it can be 1, 2, 3, 4, 5, 6. But every time you roll the dice, it will take a different value, right? Now, it's a discrete random variable. Why? Because it cannot take values like 1.5, 1.6. It's always 6 distinct values when it comes to, say, a dice roll. Now, if I were to ask if a random variable has certain values, like it can have a range of values, tell me what I should expect. This would be the formulation. And you notice immediately that we have the random variable z here. Maybe I should change color. We have the random variable z here, but we also have the probability of z right next to it. And then we have a sum here. So it means that with every value, every possible value that z could get, I will consider the probability of that value happening in the first place. So you consider the probability of every value that z could ever get if you want to compute the expectation. Doesn't it make sense? Like value multiplied by the expectation of that value plus the other value that it could take, again, times the probability of that other value, all the way to, you keep summing up until you go across all possible values of z. That tells you the expectation of yours about this random variable. So you allow for all the values that it can take. You will consider the probability of each one of those values to happen in the first place. You sum them all up. You say the expectation of random variable is 5.6. It results in a number, right? And the short form of showing all of this mathematical jargon here is the left-hand side. So E is for expectation, right? So E is for expectation. Z is the random variable whose expectation you want to compute. And you always see this. I mean, this chunk used to scare me when I started my machine learning journey. This chunk always confused me. Like, what does this mean? So it basically means that I want to compute the expectation of Z, and Z is always sampled from a probability distribution, which happens to be, we're going to denote that as Q of Z. What do I mean by sample? So every time you sample from the probability distribution of Z, it means Z keeps being assigned a value, And if that probability distribution dictates that, for example, values between 1 and 10 are more likely than values between 100 and 200, as you sample from that values of Z from that distribution, it is far more likely to see values around between 1 and 10 than it is to get values from 100 and 200, between 100 and 200. So this is important. We will use this sort of in a few parts of our derivation of the loss function of variational autoencoders today. So get comfortable with this notation. We'll see this a lot. Now, again, this was the case for when Z is a discrete random variable. It can be a continuous random variable. So remember, integration is just a fancy way of saying I'm going to sum things together, right? It's only in continuous space. It means that Z is no longer like the size of a dice that is 1, 2, 3, 4. It means Z can be 1 and then 1 plus epsilon and 1 again plus epsilon again plus epsilon. So there is no discrete sort of distance between different values that z could take. The difference between two possible values of z could be infinitely small, right? So the only difference is, compared to the previous line, we get integration here, and we get d of z here, or dz. So this basically denotes that, look, I'm going to break down z in infinitely small number of chunks. And for each chunk, I'm going to compute this, right? So again, the value of z times the probability of z, right? The summation of all of that is, again, this. So you notice that the way we show expectation is identical between the two. So this doesn't denote whether q of z is whether z is a discrete or continuous random variable, but the right-hand side does, right? Sigma is for discrete, integration is for continuous. Now, if we want to get comfortable with this, here's an example. I'm going to ask for my friend Khalil's help here. Now, suppose z is a random variable that can have one of these three values. So immediately you notice that it's a discrete random variable, right? It can only have three values. And you also notice that it can only have three values, right? So it can't take in between values, and it can only have three options. And all of these, like each one of these values, is equally likely. First of all, if we hadn't talked about expectation, so you can think of expectation as sort of average value that you could expect out of something, right? If I were to ask you, like, look, each one of these numbers is equally likely to happen, and could you give me what the expectation is that you could get out of this?
So by default, an expectation is sort of like a mean. So yeah. If that is the case, then it would be the average of the three numbers, which will be 2, 1 plus 2 plus 3, divided by 3.
Great.
Yep.
Exactly. That's exactly right. So this is let's say this is z bar, the way people show it. Z bar is equal to this, and this would be 2.
Yep.
Right? So this means that if z keeps getting values, keep generating values, it is more likely to see value 2. Right?
Yep.
Now, I'd like to sort of connect this very interestingly to expectation. Mathematically, I can do something here. Mathematically, I can play with this a little bit. Let me change color here. Maybe, yeah. Can I say this is actually equal to 1 over 3 times 1 plus 1 over 3 times 2 plus 1 over 3 times 3?
Yes, you can, but I think you wrote 1 over 2 times 2 as opposed to 1 over 3.
Sorry, this has to be exactly. Yes, thanks.
Yep. Yes, you
can. I can do that, right? Now, yes, here's the funny part. If I were to ask you, the probability of observing 1 is what? What would you say? I said they're equally likely.
So that will be 1 over 3.
Yeah. What about probability of having 2?
It will be 1 over 3.
Exactly. Again, 1 over 3, right?
Yep.
It means that observing all possible values of z is equally likely, right? Now, take a note of here. This is basically probability of observing 1, and this is 1, right? 1 itself. This is probability of observing 2, and this is the actual value 2, and this is the probability of observing 3, and this is the actual value of 3. So, and these are summations. So it is as if I have a summation here of some probability of z times the actual value of z. over all possible values of z. This is exactly the definition of expectation that we saw in the first place. This is exactly expectation of z when z is sampled from probability distribution z. So all these years when we kept, taking average of stuff, all these years we have actually computed the expectation. The only difference is the probability distribution happens to be purely uniform in that case when you want to average. It means that all the outcomes are equally likely. But we know that a distribution can have all sorts of different shapes and forms, where, for example, 1 might be 10 times more likely than 2, and 2 might be 10 times less likely than 3. In that case, these probabilities will have different values, and that is where expectation diverges from average. Right?
Interesting. Yeah.
I remember the first time I learned about this, that like averaging is actually a special case of expectation. And it blew my mind. I was maybe 19 or something. I'd never noticed this sort of division.
It's really interesting.
Yeah, very simple, but very
I picked it up outside statistics. I picked it up from a book about money, which is really interesting, a subject outside the scope of this video, but a very interesting one nonetheless. I'm happy to share that in a different session, but yeah. Let's get through the basics.
All right. By the way, guys, before I continue, feel free to post in your questions, okay? You have the chat box and you can just post in your questions. We will get to all of them. We'll do our best. Now, the other concept that this one is heavily going to be used today, okay? So sharpen your instincts. Now, KL divergence. KL divergence is a mechanism of measuring the difference between two probability distributions. How different are they from one another, right? But again, in order to understand KL divergence, there are three more concepts, or let's say two more concepts that you need to understand. One is the concept of information, and the other one is entropy. Now, if all of this is getting over your head and they look confusing, listen, this video is being recorded, right? So just let it sink in slowly, and you can go back and again watch it some other time. So we'll try to break this down as properly as possible. But don't worry if it's overwhelming. It's okay. You can come back to it later. Now, first, the concept of information. This is the formula of information, like log of probability of something, and we have a minus here. This is called information of some event X. Now, this, I'd like to sort of, ask you whether this matches your intuition. Let's say, well, we are living in Ireland, and Ireland tends to be rainy all the time, right? Now, let's say I told Khalil that, look, Khalil, today is raining. Like the event is today is raining. Now, because the probability of raining here in Ireland is really high, right? P of X will be really high, right? So negative and log of P of X doesn't make a change. So log of P of X would be really high, and negative of that would be really low, meaning that the information is not much. The information is very low. It means by telling Khalil that it's raining, it's going to rain today, I haven't given him much information. So that negative changed everything, right? But what if I told Khalil that they said it's going to be a tornado today in Dublin? This never happens. I mean, this is absolutely, I mean, Khalil is laughing right now. So this never happens, right? So the probability of event tornado is very low. So log of probability of tornado is going to be very low, but the negative of that would get a higher value. So negative of a small number is higher than the negative of a big number. So it means I gave Khalil more information, with this particular event X, right? Then again, I said that X is a random variable, so it has a probability distribution P of X. But because it's a random variable, you can ask, okay, because X is a random variable, so information becomes a random variable. So this I over here becomes a random variable, right? Because it depends on something random, right? So then you can ask, okay, so if I is a random variable, then it means I can ask, what's the expected value of I? Because X could get different values, right? So what would be the expected amount of information that I could expect out of this random variable X, out of this event X? So again, this goes again exactly by the definition of expectation that we had. The expectation of something, the expectation of a function, let's say f of x, is f of x, right? It depends on x, times the probability of different values that x could take. Right? So it's the same story. We want to get the expectation of this entire thing. Negative comes out of the sigma, so that's why the negative is here. So this negative moves here, right? Sigma of this thing that we want to get its expectation times the probability of different values that x could take. And we, again, summing over all values of x. So nothing new here. This is literally the same thing that we've talked about in the previous slide. The expected amount of information has a name. It's called entropy. Mind you, this, as a side note, this expectation could be, you could sort of sum over different values of x. Sometimes you can sum over different values over time, the expected value over time, or the expected value over different values that x can take. This is a side note, okay? So when you hear expectation, you can take the expectation with respect to different contexts. But anyway, this is called expected information or entropy, right? Now, KL divergence, the big topic that we want to understand before we can get into variational autoencoders. The KL divergence between two probabilities. This is how we show it. Probability 1, two vertical lines, probability 2, P of x and Q of x. Now, this line over here is not purely accurate, and that is why we have the notation like this. Think about it. It is as if I'm asking, okay, I'm saying how much information, the expected information that we have under Q of x, or in this probability distribution, and this is like how much information we have under Px distribution. So it's like, if you think about this formulation, on the second line, right? This chunk, you can just put Q here instead of P, would be like the amount of the expected information in Q, right? Minus the amount of information in P. So minus times minus, this already has a minus, becomes a plus. That means how much information, how much is the expected information of Q minus how much is the expected information of P. So that is what divergence means. The only thing that I'm going to change here is that the exact definition of KL divergence is that this guy has to change into P of x. That's the only difference. That is, now we have equality. That is why KL divergence is always with respect to the first distribution that you see. So here it's with respect to this guy. It means that when I want to compute entropy here and entropy here, I'm always gonna compute the expectations. Remember, both of these two are expectations, right? Entropy is an expectation. It means I'm considering both expectations over probability P. And again, over probability P, not Q, but P. It means KL divergence is always computed with respect to the first distribution. It's the first distribution here that dictates the likelihood of different values that X could take if you want to compute entropy between two different distributions. And if I want to like sort of, pack these two summations together, these last two, you can actually use the property of logarithm if you remember, one of the properties of logarithm that we had earlier was that log of a division becomes subtraction of logs. So if you have two logs that are being subtracted, you can convert it back to log of a division, right? So that is why here, if you think about it, this KL can be rewritten as we've got this chunk minus this chunk. So sigma can say the same. The values inside sigma will be subtracted. So P of X is the same. So I'm just going to factor it out times log of P of X minus log of Q of X, right? And this becomes log of, sigma Px. Subtraction of two logs based on that rule becomes what? Kelly, can you tell me?
Division.
Exactly. So it becomes the log of this division. That, my friends, is the real definition of KL divergence between two values. Now, between two distributions. Now, more neatly, this is it. It's the same formula. So again, if we're talking about discrete space, we have sigma. If it's continuous space, sigma turns into an integration. Same story. Now, one thing to note here is that KL divergence is always larger than or equal to 0. This is a crucial property that you have to be aware of if you want to understand the derivation method of the loss function of variational autoencoders. So KL divergence can never become negative. It can be 0. If it's 0, it means, remember, P and Q are identical, right? If it's positive, it means there's a difference between P and Q. The larger it is, it means the more the differences between the two distributions. Now, the last chunk that is very important is that KL divergence is not symmetric, right? So it means that the KL of P and Q is not equal to KL of Q and P. This should make sense to you right now, because now you understand that we take the expectation with respect to the first distribution. So of course, things will change. Different distributions behave differently. So the right-hand side of this formula, this chunk over here, this chunk over here will become different. P of X will become Q of X, right? So remember that as well. Any questions here before I actually have maybe I should show you the numeric example, then we can see if there are any questions. Now, we have the definition over there, right? Now, suppose P of X is the distribution on the left-hand side, meaning that it is basically telling us that, look, Z can have two values, 1 and 2, and both are equally likely, so the probability of each one of them is 0.5. So the summation of probabilities have to be 1, right? Of all the possible values of a random variable. That is why 0.5 equals 1. Suppose in one case we have QZ defined as this, where again, the likelihood of observing 1 and 2 is equally likely that is 0.5. So if we're going to go and compute the KL divergence between P and Q, according to the formula, remember, across all possible values of Z, P of Z over Q of Z will be what? 1. Because they have the exact same amount. So you have sigma of Z, P, maybe I should break down sigma, it would make more sense. So we have probability of Z being equal to 1 times log of P of 1 divided by Q of 1 plus probability of Z becoming 2, ln log, right? P of Z being 2 divided by Q of Z being 2. So immediately, this is 1. Log of 1 is always 0. So this first chunk becomes 0. Again, this is again 1, right? Why? Because probability of 2 under P is 0.5. And probability of 2 under Q is again 0.5. So it's like 0.5 divided by 0.5, which is 1. Log of that is 0. So this second chunk is also 0. First chunk 0, 0 plus 0 becomes 0. So the KL divergence between these two distributions becomes 0. It means they are identical, right? Now, let's look at the second example. Suppose that Q comes from this distribution down below, right? The probability of 1 Z taking the value 1 is 0.25, and the probability of Z taking the value 2 is 0.75. Now, you immediately see that there's a difference between P of Z and Q of Z. And if you were to compute this, you have probability of Z being 1 under P times ln of P of 1 is what? 0.5. Q of 1 is 0.25. Yeah. Plus probability of 2, which is again 0.5, times ln of P of 2, which is again 0.5, divided by Q of 2, which is
0.75.
Yeah, exactly. I mean, I might as well replace them with their values so long I'm doing this. So this one is 0.5, and this one, probability of 2 is again 0.5. Right? So immediately you notice that you don't get 0 anymore. This log is a positive number. This log is also a positive number. This results in a positive number. You can work this out, by the way, at home if you want, but trust me, this value will be a positive number, okay? And that is why we say that there is a difference, there's a divergence between P and Q, right? So that is how KL divergence works in like numerically in example. Now, this is how you can actually, but this is one of the examples of why you need to understand the math, because if you want to implement variational autoencoders, you need to understand KL divergence to be able to actually code it up. So that's important. Now, before I move to the last chunk of the basics, are there any questions?
This is very illuminating. That's all I'll say. Right. I've used KL divergence in and out, but I've never bothered to look up the derivation of KL divergence. And I used to have this intuition about it being the difference between two probability distributions, sorry, two random variables, if one probability distribution is used in computing the expectation. So essentially, you have an expectation that would be computed using its probability distribution function. and then another one, but you use the same probability distribution as the first one. Anyway, it's not fully formed in my head, but essentially it's just when I think of two random variables and I think of using the same probability distribution on the two random variables, I think of the outcome as a KL divergence. So that's how I kind of think about it.
Exactly. And by the way, if you think about this, I mean, if we want to get a little bit excited here, the KL divergence, like this sort of definition, if you think about it, is literally the expectation of this log when Z is sampled from P of Z. This is literally the same definition. So whatever value this, so you can think about this whole monster as being a random variable. So we want to get the expectation of this guy, right, is equal to, because it depends on Z, so you have to get you have to sum across all possible values of Z and consider the probability of those values coming up in the first place. So that is why the summation across all of these multiplications become the expected value of this guy. I mean, if you think about it, it is.
Yeah, it is. It is. Brilliant.
Yeah, I mean, first time I realized these things was really like, I was like, wow, okay.
Totally mind-blowing. Yeah. Cool.
Okay. Okay. Now, last but not least, very important theorem or rule that's called the Bayes rule. I'm not going to go through the derivation of it. Just take my word for it. If you want, we can go over it later on. But this is the Bayes rule. So it's all about conditional probabilities. So it means that let me give you an example before I go through the math. I think that would be much more tangible. Let's say I have a headache today, right? Then I want to figure out what's the hidden reason behind my headache. So I have an observation. Given this observation, I'd like to know the probability of having, for example, a tumor in my head. So the hidden cause, the hidden reason behind, under the hood, that has manifested itself in this observation, that is my headache. In that case, I'm asking the probability that my hidden variable, so be mindful of these terminologies, my hidden variable being tumor, given that my observation X is a headache. Right? Now, according to Bayes' rule, you can compute this probability like this. You can say that, okay, first of all, how likely is it? Like, let's say you had tumor. So given that you had tumor, let's say you had tumor, right? How likely is it for you to actually have headaches in the first place? So that's called the likelihood term. This is called the likelihood term. Remember, this guy was asking a different question. This guy is asking a different question. This guy is saying, if you had headache, how likely is it to have a tumor? This guy is saying, let's say you had a tumor, okay? How likely is it for it to manifest itself in a headache? That is X, observation. This guy is the probability of having a brain tumor, right? Regardless of any observation, like in general, how probable is it for a person to have a brain tumor? So it's, as you see, there is no X there's no observation. It's just across the board, how likely is it in general to have a brain tumor? because it's basically because it's like prior to seeing any observation, prior to seeing any X, because the word prior is key there, this is actually called the prior probability over my hidden variable Z. That is having a brain tumor or not having a brain tumor. And this guy, this division, is probability of having a headache, right? Having a headache in general. So again, this has not, you see, this guy has nothing to do with the hidden reason behind the headache. This says in general for a human being, how likely is it for them to have a headache? This term is called evidence. And if we were to combine all of these terms together, likelihood times the prior divided by the evidence, we get this guy, the answer to the original question. Because we can compute this guy only after having seen an observation, posterior to seeing an observation, that is why this probability is called the posterior probability. So you'll hear these terms a lot. What is the prior distribution? What is the likelihood? What is the evidence? What is the posterior distribution? This is what they mean when they talk about all of these things. Before I move on, I'd like to point out one very important thing. And it's that the evidence, probability of evidence, let's say I have a headache now, right? The probability of having a headache in general. Because a headache can have infinite number of reasons, right? It means there are infinite number of possible causes behind the scene. Because of that, it is intractable to compute this value, this evidence. This is the sort of, curse of Bayes' rule, let's say. You hear this a lot, that the evidence is intractable. It is because this evidence is across all possible, hidden causes that we have marginalized out. So if you want to be really real about this, it's like probability of having a headache, right? Sorry, probability of having a headache given that, for example, given Z1 times probability of Z1. Like if Z1 was to be, for example, having migraine, what is the other reason? You can have headache if you have the reason Z2, the Z2 could be some other disease, times the probability of Z2. You could have all the way to like infinite number of Z's could be the reason. Now, if you want to marginalize these out, all of these Z's out, and get P of X, so P of X mathematically is equal to the integration, like infinite number of estimated integrations together of P of X Zi times P of Zi D of Zi. So like the one integration is across Z1, one is across Z2, one is across Z3. So the reason we have this integration across all of these Z's is because we want to say, look, the probability of having a headache in general, so I'm going to consider all hidden causes across all of their values. So Z1 here, when I say integration over Z1, it means I'm considering all possible values of Z1. So remember, this is a nested integration. That's the curse. It's like you have infinite number of nested loops in a code. It's not possible. You can't compute it. That is why they say evidence is a curse. You cannot compute it because you can't, in a real life situation, you can't compute this because you don't know all the hidden reasons for some observation. Because of that, they say computing the exact posterior is intractable. So then they resort into other mechanisms to compute the posterior probability, mechanisms such as Monte Carlo sampling, such as Gibbs sampling, and the one that we're going to work on today is variational inference. Okay, and that would be the main thing that we're going to do today. Now, these were all the basics of the loss function computation and calculation of variational autoencoders. You need to know basics of logarithm, expectation of random variable, KL divergence, and Bayes rule if you want to understand the derivation. Now, before we continue, I noticed that it's been already 1 hour. And the derivation, I think I can wrap the derivation up in maybe 15-20 minutes. Should we keep this for some other session, or should we go ahead? What do you think, Khalid?
I think a lot has gone into this, and I'm completely mind blown. Just for the record, like,
okay,
everything you've talked about, I
Yeah.
have known for many years, over a decade, but as you've teased them out little by little, I'm finding my neurons, firing, making new connections. And I'm just kind of rethinking some of the priors I had, in essence.
Nice, some of the priors. Nice.
Yes. I want to say, maybe we should take a breather, not because we can't take more, but because, this is where it's just a natural place to stop. It's so beautiful. Like,
yeah. Absolutely agreed.
I'm thinking the two exciting bits in there is KL divergence and Bayes rule, even without defining it, deriving the Bayes rule. Your analogy makes a lot of sense, and it's kind of, I'm thinking in terms of like tables, in terms of number of records, and then applying filters. So what's the probability of getting a headache given that you have a tumor, and the cost of computing likelihoods? But I haven't fully formed, like, based on your explanation, I'm rethinking what I understand about Bayes rule, because what I thought was that given an evidence, or given a prior, basically, not an evidence, I need to be clear on my vocabulary. Given a prior, you update the prior with an evidence to get a posterior. That's what I was thinking. But what I'm getting out of this right now, and that seems to be the correct thing, which means my understanding of it was wrong, is that given a prior, you get a likelihood to update your prior. The evidence, which is a marginal probability.
Sorry to interrupt you. So
yeah.
Saying something like given a prior, I'm not sure what you mean. Are you
so if I have
given X?
A prior would be, my thinking would be my current state. So when I say prior, what I'm saying is, let's assume, so the way I think about Bayes theory, and this is off script, everyone, this is just Mehran trying to correct Khalil's thinking out loud. My thinking about Bayes theorem is this: you have a belief, you have, a sense of understanding of a current state. That representation is informed by whether some experiment or just, it's just a state, so it's a belief. When you encounter new evidence, you update those beliefs.
It's just, so one sort of, just so we are using the same terminology, it's
Yes.
once we get a new observation, we
Okay.
update our beliefs. So evidence is probability of an observation.
Got it. Evidence is the probability of an observation.
So in other words, when you have certain belief about the world around you, let's say,
yeah.
That is your prior belief about the hidden variables, P of Z, basically, hidden variables around you. Given every time you get an X about the world, you get an observation from the world,
yeah.
you sort of correct your prior into your posterior, a better and better posterior. So you can say that my posterior after seeing observation 1 becomes my prior for when I see observation 2. It's like sort of chained together all the way up.
Yeah. Okay, that makes more sense now. So I was kind of getting my vocabulary there mixed up, but that's kind of thinking I have in there. But when I think of observation, I normally replace it with evidence. And you can see how confusing it is where you describe the denominator of that equation as an evidence, but that evidence is intractable to compute based on your explanation. So that just kind of challenged the way I was thinking about it. And the fault of my thinking is that I would take observation as evidence as opposed to an observation just being an observation, which might actually be evidence or not, but it's just a new piece of information that updates my prior.
Yeah. The reason they call it an evidence is because, remember, when you say that the probability of a given observation for you, let's say you have a belief about your world, right? And you see, let's say your observation is that, okay, a fish is flying in the air, right? Let's say one day you saw a fish flying in the air.
I must have been really high then.
That could be one explanation for sure. But the reason it's called an evidence is because whatever belief you have about the world is under a model that is your brain. So everything, all probabilities that I talked about today in Bayes' rule, if I want to be really concrete, everything is conditioned over my model of the world, right? So when I say P of X is evidence, it means evidence for my model of the world. If seeing a fish in the air is my observation, probability of seeing a fish flying in the air under my model is very low. It means that observation X provides the least amount of evidence for my model being a correct model of the world. But if I see a fish swimming in a pond, so the probability of observing a fish swimming in a pond is very high. Right? So the evidence is very high. It means this observation is a very good evidence for your model of the world because you were not surprised. By the way, you can also sort of connect this evidence to information, the notion of information. So if something has a huge evidence, it means it's least surprising or least amount of information it has. Remember, evidence is P of X, but information connects to minus P of X. Technically log of P of X, but I'm just going to get rid of that. So that they're inverse of each other, right? So if for example, if observing, let's say a fish in the air, if that's what you see and under your model, it's so weird. So it means your model really needs to change.
Yeah.
Right. And remember, if P of X, because X is very strange, P of X is very low. Under your model, seeing a fish in the air should be very low, right? Because it's very low, minus that becomes high. It means it has a lot of information for you, right? And so they also call information, they also call it surprisal. So if something's surprising to you, it means it has information for you.
Yeah, got it.
Yeah.
And this is why it's good to take a pause here, because I'm going to let it simmer for a bit, and then I'm going to rewatch it again, even though I was here, so that I can plaster and cement those concepts into my head, because you can't imagine how many times I've had to explain these concepts and I struggled, not because, I haven't seen them before, but because my understanding was not unadulterated and as neat as it is from this session. So I would say this is my best session so far. So, so I'll probably
Nice.
bookmark it and revert again. And I guess, you know, it makes sense to take a pause here. I hope
Yeah.
if you're watching this, you're having this kind of experience. I feel at the moment I'm thoroughly mind blown. So yeah, thanks for that explanation.
No worries. It's actually, so this is something that the reason I've got into all of these things and understanding all these things is because, funny enough, all understanding these mathematical fundamentals connect really well in certain lines of research at the moment in the world. The lines of research that investigate the intersection between AI and neuroscience. So everything that I said, like Bayes' rule can be used to mathematically model perception, like humans' perception of the world. It can, so the concept of surprisal, information, entropy, they can be used to mathematically model the decision-making process of us as humans in the world. That is why I keep insisting on understanding these mathematical fundamentals, because once you understand them, you realize that you can get a better understanding of a variety of highly hot topics, both in the industry and in academia. So whoever thinks that they can just use some off-the-shelf model and do what they want to do, I think first of all, they're robbing themselves of a huge opportunity to understand the possibilities out there. And second of all, they might attribute certain failures in their code to the wrong reason because they don't understand what's happening under the hood. So the probability of the hidden reason given the failure in their code would be highly intractable for them. They can't understand what the real reason is. I remember this one time I was talking to, a few years ago, to a researcher who had just used a convolutional neural network off the shelf. He had found it on GitHub and then used it in an assignment of his in his machine learning course, I think. And no matter what he did, the results were terrible, right? I kept asking him questions and I realized that he doesn't know the answer. And then I realized that, oh, you're training your network for like 5 epochs, like very short amount of time. And I said, okay, let's visualize your loss. And the loss had not converged, nowhere near convergence. And then I realized his optimizer is SGD, like 5 epochs SGD, like stochastic gradient descent, is nothing. So I've made a few changes to the code and made a few changes to the convolutional neural net, the activation functions, then it started to work. Had I not understood what's under the hood, I would have never been able to make those changes informatively. So that's why, to all of you out there, do not buy into the myth that you can just use an off-shelf model and you will never face a problem. The problem is you will face a problem when it might be a little bit difficult to recover from the problem.
Absolutely.
Okay?
Absolutely. Like I've had a similar experience as well in a previous job where this person was trying to get a model to fit a particular data, so a particular problem, and essentially it's just to solve a problem. So the model wasn't just the issue; it was more like, you know, just find a model that solves this problem, minimizes the error. And after a few months, this person had struggled so much, and it began to raise suspicion about their competency, where in reality, you know, it's more like there are problems that are unsolvable even by machine learning problems. But in this case, in other industries, people have solved this problem. So they brought in someone who was significantly smarter than all of us in the team to have a look into the model. And he looked at a few candidate models that had been looked at, and he said, ideally, all these models should work. The problem there was that the loss function was wrong. And that what we had, or what that particular person had, but us as a team, because we couldn't help that team member as well, what we had was that the loss function we had was quite close to what it should be, what the ideal should be. But because that particular person, we didn't look at the loss function, but that particular person didn't even understand the loss function well enough to tweak it to the particular problem, the company wasted many months into it. And lo and behold, a slight change here, a slight change there, and it worked like a charm. So anytime I have an opportunity to look under the hood, I cherish the opportunity. And again, we had this conversation just about last week with someone I know who was saying that in the future, machine learning, applied machine learning scientists and applied data scientists will be replaced by AutoML. And we went off back and forth, just kind of debating because, there's been a lot of progress in AutoML. And I said, yeah, I can give you edge cases where AutoML will struggle, or instead of solving the loss function in there, what they do is they stack a lot of models, creating this really massive model that essentially just learns fragments. Each model kind of fits a fragment of your data, and once it gets to a problem that it can't generalize to, it falls over. You don't get that out of AutoML. You get that from people who really understand what they're doing. So not always black box, sometimes gray box, if possible, white box. Yeah. I think you're muted.
Sorry.
That's fine.
I was coughing, so I muted myself.
Okay.
That's exactly true. Totally agreed. Rakesh Kumar also suggested that we keep the actual derivation for the next session. So that's what we're going to do, by the way. He has also asked, is it all going to be there forever, or you will remove it after the session?
Let me answer this.
Yeah.
I won't let him remove it because I'm going to come back to this video over and over again. Okay. So
but I didn't get what he means.
The video, I guess.
Yeah, the video is going to be uploaded, of course.
Yeah, it's going to be there on YouTube forever.
Yeah. It will be there forever.
That's how good it was. So yeah.
Oh yeah. Oh, sorry. Now I understand what he means, because we're gonna do it for the second part in the next session. That's why. Okay, gotcha. Sorry. Yeah. No, this is gonna be there. I'm just gonna change the title to part 1, and then the next one, part 2. Actually, it's good because in the part 2 we will derive the whole thing, and I can also, because I will have enough time to also talk about. Okay, here's the loss. You see the big formula. Here is how you can implement this in a variational autoencoder with a figure. I can show you each term translates to a part of the variational autoencoder. And then after next session, I think we should be able to start coding.
Yes.
Oh, yes, exactly. Okay, that's great. Thanks to everyone who sort of soldiered on with us. I hope that this was informative and not too overwhelming. And like always, I've posted the link to the ML Dons Discord server in the chat box. So do click on that and join us. So you'll be notified via different announcements that we have. We post different articles, studying material and announcements for the events that we're going to have. Plus, we want to make a nice and friendly sort of community of ML Don over Discord. And also, you can feel free to follow ML Don on Twitter, Instagram, and also visit the website, mldon.com. There are cool blog posts over there. And thanks a million to Khalil again. It's really nice to see you and have you in these sessions.
The pleasure is all mine. I wouldn't miss it for the world. So thanks again for having me.
Appreciate it.
Yep.
Thanks. See you later, folks.
See ya.